Hi, my name is Masumi Shafinejad and I'm presenting my work on PCOR, Private Contextual Outlier Release via Differentially Private Search, which is a work with Florian Kirschbaum and Ihab Elias from University of Waterloo. First, I'm going to define the problem that we're working on. Then I'm going to mention the challenges that we faced and the solutions that we proposed for this problem, and then I provide the results. So in our problem, we work on contextual outliers. And to talk a little bit about that means, I provided these two examples of imagine a database of temperature recordings, and I tell you that we have 28 degrees there, and I ask you if that's an anomaly. And a very reasonable question to ask there is, what is the context? If that data records are from winter days in Alberta, which this 28 degrees is definitely an outlier, or these are summer days in California, which means that this 28 degrees is not an outlier at all. So with that background, contextual outliers release is when we query the database with a particular individual that we have in mind, a particular data record, and we ask the data analyst to give us the context in which that particular record is an outlier. And by context, I mean the set of attributes that define a subpopulation of the data records that we have. Let's say doctors who are in Toronto or Ottawa. So let's step back a little bit and talk about what are the motivations for revealing the context. Revealing the outliers with supporting the context. So we might have approval or disapproval motivations there. In approval, imagine when we want to give awards to people with particular achievements, we want to see the context or the subpopulation or significance of the achievements of people. So we need to know what is the context or what is the population that these outliers are defined in. And there might be disapproval motivations behind there too, because imagine intrusion when we want to find anomalies of like malfunctioning or intrusion. We want to know that what is the significance of this malfunctioning. And I want to emphasize that in our work, we are not thinking about protecting the outliers. We do want to reveal the outliers because of the motivations that I said. We want to protect the non-outliers. So because of revealing these outliers, we need to say something about the context, the attributes of the subpopulation that this record is an outlier in. That might reveal information about the non-outliers, and that's what we want to protect in this work. I have an example of this privacy leakage here. Imagine a data set that I have being consisting of attributes job title, district, and city, and the numerical attribute there be the salary information. And for job titles, you have CEOs, medical doctors, and lawyers. We consider the cities Montreal, Ottawa, and Toronto. And we consider the districts business, historic, or diplomatic that people live in. And imagine that I report an outlier there. We have a particular data record V that I say that they are an outlier and a set of CEOs and lawyers who live in diplomatic districts of Ottawa. But imagine that you have some side information and know that there is just one CEO living in diplomatic district in Ottawa. So this information that I gave you reveals information about this particular person. And there is a privacy leakage that I showed with this extreme example here. And I want to emphasize that the outlier finding algorithm is not hidden. So we know that by seeing this information, we can guess some information about who, like the salary of the CEO. To give a little background about related work, I want to mention that the works that are considering outlier detection are considering privacy for outliers. There is crowd blending, there is tailored differential privacy or outliers in the subspaces, which all address the problem of privacy for outliers. or there are some who consider privacy for all, and there is this work layered privacy, which considers less privacy for outliers. There is no work that is considering protecting the context. And for that, the privacy measure that we are looking at is differential privacy, because this is a privacy guarantee for individuals, and that's what we're looking for. It gives us bounds on privacy leakage. We can measure what's privacy leakage that we have by epsilon parameter, and it's been used in a number of applications, and it's shown its efficiency in US Census Bureau, in Google, Apple, and Uber applications as well. And the idea behind differential privacy, as I show in this picture, is that if you remove one record from the dataset, if you see this green record is the difference between these two datasets, the answer that you give to the query analysis is the same. So by looking at the query answer, the adversary won't be able to tell if a particular individual participated in the study or whatever that data collection mechanism was or not. So, okay, so we know that what's the problem. We know that we can use differential privacy there, but what is the problem? The problem is when we're working on privacy, we have these trade-off between privacy utility and performance. So we need to have a good notion of privacy that is meaningful. And at the same time, we want to have a good utility, we want to have useful answers. We don't want to get like just random answers that sure provide full privacy, but like they're random and not useful. And we also don't want it to take forever for all this to be calculated. So the performance matters to us too. With that in mind, I would like to say a little bit about the mechanism that we are using for differential privacy. We're using exponential mechanism, which is a common way of providing differential privacy when we're dealing with non-numeric attributes. But then what exponential mechanism does is brute forcing in all possible solutions that we have, which is the context here. So when I say context, imagine the attribute values that I have. So if I have job titles, city and district, and each of them have three possible values, brute forcing among all possible contexts means brute forcing among these 2 to the power of 3 plus 3 plus 3, which is to the power of 9. So what exponential mechanism does is brute forcing among all of these and scoring the context based on the utility that they have and select among these weighted contexts. So the challenge here is the exponential mechanism's time complexity. So as you see, like this is exponential, and for a data set of size just 50,000 with 25 attribute values in total, it took us 3 days to go over all these contexts. So the challenges that we have, if I want to summarize them, is that how we can define differential privacy there. I'll mention that we're going to use a variant of exponential mechanism because we can't just use it in its original definition. Complexity reduction is important to have performance there. We want to have high utility, and at the same time that we want to have a good privacy and scalability. We also want our design to be compatible with any utility function or any outlier detection. So what's the solution that we are offering? So first of all, for the differential privacy notion for PCOR, we need to use a variant of the exponential mechanism because in outlier detection in particular, if we want to introduce an alternative context instead of the true context, which has the similar utility, and these will be more clear when I talk about it, this context still needs to be a valid context for the data point that I have. So, which means that the data point still needs to be a valid outlier in the second context too. And that's a restriction. And for that, we are using output constraint differential privacy definition, which means that, which guarantees that this context is going to be still a valid context. And for complexity, what we were considering was how about using sampling? There are works that show that if we sample when using exponential mechanism, the privacy budget that we need is just twice as the time that we don't use sampling, which is good. There's not much sacrifice in privacy there, but the problem is it does not reduce the complexity if I need to just sample from the set of context that we have. So we were thinking how we can make the sampling cleverer and reduce complexity with that. We noticed that we have locality in valid context. And let me talk about it a little bit. If I show the context by a vector of zeros and ones, with ones showing appearance of one particular attribute value and zeros showing that that attribute value is zero. So let's say that if I have jobs of medical doctors and lawyers and professors, and if I'm talking about someone who's a professor, or if I'm talking about a subset of professors and medical doctors, then the vector showing that context has two ones for professors and medical doctors and zero for lawyers. Let's imagine that we show these contexts with these vectors, right? We observed locality in valid context, which means that if a data point was an outlier in a context, if there was this other context that was different from this original in just one bit, then there was a high probability that this data point was an outlier in the second context too, or at least a probability more than just a random sampling. So the idea that we had that we can't just map this to a graph search. So we can have those contexts as those vectors that I said as the nodes of a graph, and two nodes are connected to each other if they're different in just one bit. And we're thinking that because of this locality, we can just start from a valid context, and this is going to be a search from that original context. We started with random walk, and we proved that if we start from original context and go randomly through its children, the complexity will be polynomial, and the privacy budget that we need is just twice as before. And I want to say that, like, I using these tree structures here for just simplicity. The structure, the graph structure, will be more complicated than just a tree. And then, as alternative, we also looked into differentially private depth-first search and breadth-first search as well. So this is the first time in the literature of introducing these two searches in differentially private manner. We proved that if we are sampling, if you're using these searches for sampling n records, the privacy budget that we need is n times the privacy budget of non-sampling version. And the complexity is, again, polynomial. Same goes for breadth-first search. And then we put all these into experiments. The sampling candidates that we looked at was just uniform sampling, random walk, differential private version of depth first and breadth first search. And we looked into different outlier detection algorithms. There are three main categories for outlier detection, and we picked a well-known candidate from each of those. We picked grubs, local outlier function, and histogram. And for utility function, so how to score this context, we looked into two merits. First is the population size of the context, and the other one is the overlap with the original context. The first one means that the bigger the population size is, the more it shows significance of an outlier, and that's what we are looking for. And the second one says that we have the particular context in mind, the more overlap the other context, the alternative context has with the original one, then that's the more desired one. And we looked into two data sets for our experiment: the Ontario's public sector salary with attributes of job, employer, and year. There are 50,000 records, 25 attribute values in total. And we looked into murder accountability projects data sets, the homicide data set with attributes of weapon, agency, and state with 110,000 records and 12 attribute values. And I'm going to show you the results here, that the epsilon that we're considering, and this is the final epsilon. And remember that when I said that the epsilon of breadth source would be n times an original epsilon. So this n times something is this 0.2 here that you see. The results show that the BFS algorithm does the best in timing and utility, and with a great epsilon to epsilon 0.2. For people who are familiar with differential privacy, it's ideal to have epsilon that is like smaller than 1 as a metric. We did run experiments with other algorithms as well, in addition with to LOF. So GRUBS and histogram, they show the same, that BFS does well in providing good utility, providing privacy while it's keeping good utility, close to 90%, with good timing as well. We also ran other experiments on seeing what is the effect of privacy parameters. So we tried it for different privacy parameters, and we saw that like there is the effect of that on utility. The more you want privacy, which means that the smaller the privacy value is, you get less utility, which is a trade-off, and that's what we expected. And we also saw the effect of number of samples on performance and privacy. So the more the number of samples are, the privacy that we need is the privacy that we can guarantee is less. We get higher values of epsilon, which means that the privacy is less. And then the utility that we get generally gets higher, but there is some point that there is the best point, and like it's not that we can increase the number of samples and we get better utility directly. There is just this best point that shows that's shown with this 0.9 here. And with that, I conclude this work. This was a work of seeking a private, accurate, and efficient solution for the problem of providing privacy in contextual outlier reporting. It was the first time of introducing differential private graph search algorithms, and this can be extended to other works in database analysis. There is the chance of directly using this work for wherever that we have privacy revealing database queries that have locality property in their output. With that, I conclude my work, and thank you for your attention.